Start.
Thank you. Yeah, first of all, sorry, I have a bit of a cold, so my voice is not maybe as clear as it usually is, but I'm going to try to talk as clear as I can. So this is joint work with Bahareh Afshari, my supervisor. It's a bit overdue because I carried out, most of it before my maternity leave. So if you've seen a talk on this almost, 2 years ago, that's correct. But now all the proofs are down and it's open. So let me first explain, the words in the title, starting with the modal calculus. We've seen maybe already some examples like PDL, but in general, in fixed point logics, we have formulas that satisfy an equivalence of the following form. So we have psi, and it's equivalent to if we plug psi into some other formula, phi. And a nice example is a formula like A until B in temporal logic. So A until B is true if either B is already true now or A is still true and tomorrow, also next, the operator we have here, A until B is true. And now in the modal mu calculus, we have explicit operators to add these kinds of fixed points to our logic, one for the least and one for the greatest fixed point of a formula. And this logic is very expressive, but it's also very well behaved. So it's decidable, it has a small model property, we have planetary axiomizations, uniform interpolation, many nice things. And we also know from the proof theoretic side that non-well-founded and cyclic proof systems have proven very successful in characterizing this logic in a syntactic way. Now, lately, there is an increased attention towards fixed point logics over a intuitionistic base. So some examples, not an exhaustive list, intuitionistic linear time temporal logic, common knowledge logic, or lot logic. Just some references here, mostly in the context of non-well-founded proof theory, but certainly there's also more out there. And now the general aim of this project is to develop some kind of general framework and proof theoretic techniques to study this kind of intuitionistic modal fixed point logics. And so far, together with Graham Lee and Lucas Singer, we've looked at proof systems for intuitionistic LTL and intuitionistic modal logic with the master modality. And now we're doing kind of the next step. So we're doing the full mu calculus, but an intuitionistic version of it, where we have one universal operator, which is the Lewis arrow, which can be viewed as a generalization, actually, of the modal box. And I'm going to provide game semantics and a non-well-founded analytic proof system for this logic. So a bit of an introduction to the Lewis arrow. So this is actually the historical ancestor of the box. So dissatisfied with material implication, Lewis introduced several axiom systems. So this is S1 to S5. Some of these names we're still using, S4 and S5, meant to formalize a notion of what he called strict implication, which should mean something like psi can be inferred from phi. For the modern modal logician, you can think of this arrow as saying box and then phi implies psi, where now we have the classical implication on the right side. And classically, you can define box in terms of this arrow and also the other way around. So we ended up just using box because it's a lot easier. But in the intuitionistic setting, these things are actually not interdefinable, and the Lewis arrow is more expressive, and this was first noticed in the context of provability logic by Rosalie Imhoff and Albert Fischer. And there the arrow is used to model properties like preservativity. All right, so a bit of the overview of what I'm going to do. I'm going to introduce the logic, provide game semantics, show our result that this logic has the notion of guardedness, which is also true for the classical modal mu calculus, then provides a non-well-founded proof system and some concluding remarks. So to start with the logic, I think nothing too surprising here. We have all the connectives. We have an intuitionistic propositional logic. Then we have our modality, which is the Lewis arrow, and we have our least and greatest fixed points. Overall, positive formula, so weakly positive here. And we need always, as always in an intuitionistic setting, both the least and the greatest fixed point operator. In this presentation, I'm restricting to formulas that are clean. So to each bound variable, we can associate a unique fixed point formula. This is just a choice of presentation. It's not necessary, but I think it makes the game semantics and the proof system a bit easier to read. And moreover, to keep track of the negative or positive formula occurrences, it will be very useful to make it explicit when we talk about formulas or subformulas, what kind of polarity they have inside another formula. So in particular, this is important when we're talking about implications. So when we take the subformulas of some implication, either it's the intuitionistic one or the modal one, you see that the polarity of the antecedent swaps and of the consequent stays the same. All right. So for the relational semantics, we use bi-relational Kripke models. So we have our intuitionistic relation, which is a partial order, our modal relation, and then we have a property called triangle confluence. I'll say a bit more about this in a second. And then the truth relation is, I think, what you would expect. So I left out the standard connectives, but we have our intuitionistic implication. So here we have to take all intuitionistic successors into account when we're evaluating the implication. And we actually do exactly the same for the Lewis arrow, right? But then for the modal relation. So something I like is a bit of the symmetry here between the two relations. Of course, there's the difference that, oh, I think, did I mention this? No. So the valuation is monotone with respect to the intuitionistic order. This is not on the slide, my apologies. So there is an important difference between the two implications. Yeah, that's unfortunate, but I hope that is clear. Oh yeah, and then the fixed points are interpreted as the least and greatest fixed points of the function induced by the underlying formula. All right, so a key property of intuitionistic Kripke semantics is that we have monotonicity. So if we move upwards in the intuitionistic order, we should preserve satisfiability of formulas. And this is exactly what the triangle confluence gives us. So triangle confluence is the following. If I go up in the intuitionistic order and then take a step in the modal direction, I should also actually have a modal relation between these two worlds. So that's what the dotted line means. If we were to restrict to just box formulas, so only occurrences of the Lewis arrow where you have a top on the left, this fourth down confluence property would suffice. But there's actually a nice lemma that says that if we just look at the triangle models, we are also getting all the box validities. So by looking at triangle models, we are implicitly also studying the box fragment. I'll mention this later as well. So this was already noticed by Rosalie and Albert as well, but it also holds in the fixed point case. So one important note, so the Lewis arrow formulas are not monotone over this weaker condition of fourth down confluence. So it's not hard to find a counterexample to this. So this actually really shows that we have a more expressive modality here than if we just had the box in the intuitionistic setting. All right, so let's have a look at the games. So given a model and some clean formula psi, we can define the evaluation game between two players. I call them Eloise and Abelard, or exist and for all, let's do that. And the intuition is that exists wants to show that the formula is satisfied if we have a formula psi here with a positive polarity, while for all wants to show the converse. So the polarized formulas here enable us a very nice, I think, presentation of the game. I only wrote here the positive formulas, but if you have negative ones, you just swap the roles. Okay, so let's see what's happening here. So I think for the conjunction and the disjunction, nothing too surprising. So for the conjunction, for all has to choose which of the conjuncts are we going to falsify. For the disjuncts, X is going to decide which of the disjuncts are we going to satisfy. For the implications, we need an extra step because we need one step to pick a successor, either intuitionistic or modal, and then we need one step to break down the formula. For both cases, actually, it works the same. So, but let's look at the intuitionistic implication. So, first, for all has to decide at which intuitionistic successor of S are we going to falsify the formula, and then X is going to say, well, this next world either falsifies the antecedent or satisfies the consequence. So that's why we need these two steps, just for a bit of bookkeeping. And then we can use the polarity in a nice way to then swap the roles of the two players. Oh yeah, maybe I should say something about the fixed points as well. So when we hit a bound variable, we can just replace it with the unique fixed point formula that is associated with this variable, because we have chosen this clean presentation of fixed point formulas. And if we hit a fixed point formula, we just break off the binder. Okay, so if we have a game which starts at a particular position Q, I'm denoting it in the following way. And then a play is an infinite sequence of positions according to the rules that I just gave. And a full play is either infinite or it ends in a situation where we have no admissible rules. And finite games would be lost by the player that did not have any more options, so who got stuck. And then the question is, what happens with an infinite game? So if we have an infinite play, we need some way to decide who the winner is. And in an infinite play, you can show that there will always be some unique, most important, or let's say outermost bound variable that is occurring infinitely often in this play. And I will not give the precise definition here, but you can think, if you're looking at a fixed point formula, it's the binder that occurs more outside of the scope. But otherwise, let's just say there's a most important fixed point variable. And moreover, this variable will have a well-defined polarity. And this is due to the positivity constraint that we have. So then we can say that an infinite play is one by exists if this most important bound variable is either a negative mu variable, so it has a negative polarity and its binder is mu, or it has a positive polarity and its binder is a new variable. So here the idea is, of course, it's okay to unfold a greatest fixed point infinitely often, and it's not okay to unfold a least fixed point infinitely often if you're trying to satisfy it. All right, and then we get our theorem stating that the game semantics is actually sound and complete with respect to the relational semantics. And this is in essence just based on the classical case. I think what this really makes the proof adaptation work very smoothly is this presentation of the polarized formula, so being very explicit about this polarity. First I try to do it without it, and then things become messy. So it's mostly the presentation here, I think, that I want to sell. Okay, then moving on to the next topic, which is guardedness. So in the classical model mu calculus, we know that every formula is equivalent to a guarded one, which means that the fixed point variables that the binders are quantifying over, we can assume that they occur in the scope of a modality. And this gives us an easy way of obtaining progress, because whenever you unfold and you break down the formula until the fixed point variable, you always cross a modality. So in our case, this is the equivalent of that. So a variable is guarded in a formula phi if it occurs in the scope of some Lewis arrow, either on the left or the right side, doesn't matter. And then a formula is guarded if for every fixed point subformula the variable is guarded. And then we have the following nice result, is that for this logic, every formula is equivalent to a guarded one. And I think the proof is quite cute. So at least for me, intuitively, in the classical case, this is true because just adding fixed points to classical propositional logic doesn't give you anything new that's already expressible. You really need the modalities to get something new. And now this is also the case for IPC, which was proven by Ruitenberg. And this is not even close as obvious, I would say. I mean, in classical propositional logic, you have, if you start with a finite number of propositional letters, you have finite number of truth values that you can get. So if you start unfolding, at some point you need to get something that's equivalent. This is not the case in intuitionistic logic. So it's at least, for me, surprising maybe that this is true. The proof is also, not trivial at all. And you can use this to show guardedness for this logic as well. So the trick is quite cute, I think. So you prove it by induction. Of course, the only interesting case is the fixed point case. And then to get rid of the unguarded instances of your variable, you use Ruitenberg's theorem. So you put fresh variables for modal and fixed point stuff. Then you're inside IPC again, so you're allowed to use this theorem. You unfold for as much as you have to according to this theorem, and you can replace the unguarded instances either by a top or a bottom, depending if it's the least or greatest fixed point. So that's nice. So we are allowed to, well, restrict ourselves to the guarded fragments, at least if you care about just treating all validities of the logic. Of course, there might be a lot of blow up here because you are unfolding and stuff like that. But yeah. All right. Then let's get to the proof system. So for me, a sequent is a finite set of polarized formulas, but we can present them in the more common way. So all the minus formulas are on the left, the right. I made a mistake here, I think. Yes, okay. So the gamma should be the minus and the delta should be the plus, right? Maybe I should not have said it and see if someone's paying attention. Okay. So then the propositional rules are just a standard multi-conclusion calculus for IPC, so nothing surprising here. So it's the right that is where we restrict and where we make it intuitionistic. Then the modal rule. So the Lewis arrow is a bit of a strange beast. This rule is sound, so let's just think about it for a second. So if we want to prove that A implies B, well, if A already proves B, then I'm happy. If A does, let's say that it doesn't prove B, but it proves C, but then I know that C implies D, then from A and D, and then from A and D I can get B, then I also get the implication. So this is sound. For completeness, we need the generalization of this rule, which looks a bit atrocious. There's nothing very deep happening here. It's just that we need to consider all possible cases. So we need to include all Lewis arrows that we have on the left. And then we have, okay, for each of these Lewis implications, we have to decide, are we going to satisfy the antecedent or falsify the consequence? So if we have n implications, we get 2 to the n options of how to define them. So this is what the sets, like the math call D and C's are doing. So they're ranging over all possible sets such that the following is true. So for each implication, we're Lewis arrow, we're picking either the D or the C. If you don't care about the Lewis arrow and just care about box, you can just think of the standard box rule here, and that works as well for the box fragments. Okay, so the fixed point rules, because we have these clean formulas, they look as follows, right? So we just break down the binder, or we replace the bounded variable by its fixed point formula. Okay, so these are our rules. Then, yeah, derivation is then a tree labeled according to these rules. We're allowing infinite trees as well, so it's a non-well-founded system, right? And then to say what is a proof, we need to talk a little bit about traces. And I, of course, don't want to make this definition precise. So either you know what it is or you don't, and then I'm going to try to give a very high-level explanation. So a trace of a formula through a proof. The idea is that you pick a formula at some point, and then you trace how it is broken down by the rules along this branch. So it can be a side formula and then nothing happens to it, or it's a principal formula and then you're actually breaking it down. And for us, it's also important that, yeah, we keep track of the polarity, right? So if you're switching to the other side of the sequence, you have to record this as well. And then just as for the games, every non-stagnating trace, so that this doesn't get stuck on the same formula at some point, we will have this unique most important or outermost bounds variable that occurs infinitely often, and this will have a well-defined polarity. And then a derivation is a proof if every infinite path either has a negative mu trace, so trace with negative polarity and mu binder, or positive new trace. All right, okay. Then soundness, we prove it with respect to the game semantics. So actually the work has already been done there because the step from the normal founded proof to the game semantics is not as big anymore because the presentation is quite similar. Then for completeness, we do have to do a little bit more work. We're proving it with respect to guarded formulas. And by our guardedness results, then we get at least an indirect full completeness result. And the proof sketch is as follows. So we follow the Nowinski-Walukiewicz idea that we construct a validity game, which will be omega regular and therefore determined. A winning strategy for prover will correspond to a proof or to a regular proof because it's an omega regular game. So the winning strategy that you get for prover will have bounded memory, and you can actually use this to show that the proof will be regular as well. But yeah, you can forget about this. The main thing is that we get a proof. Then the winning strategy for refuter will induce a pre-counter model. And I say pre-counter model because we have this triangle confluence property that we have to worry about, right? So the standard way that you get a counter model from a winning strategy for a refuter is that whenever you go through the right implication rule, you're creating intuitionistic successors. When you go through the modal rule, you're creating modal successors. But now we have, wait, I should do it for this way, to actually make these two kinds of relations satisfy some confluence property. And that's not what comes from the refutation itself yet. So you have then the next step of forcing this pre-counter model of actually being a model in what your definition is, and for us now that's triangle confluence. The nice thing about triangle confluence is that you get this very easily, I would say. So all you have to do is replace the modal relation by the composition of the intuitionistic order and the modal relation. And what you're doing here is adding in extra modal relations. So you don't have to worry about breaking monotonicity because of that. And because we only have a universal modality, we're also not breaking falsifiability of the formula that we care about, right? So we're building a counter model. If you would have diamonds, then maybe adding in extra modal relations would break the fact that you're trying to falsify a particular formula. This is all very sketchy, of course, but I know the people who work with this are nodding. Otherwise, let's keep it very high level. Okay. Oh, yeah, running out of time. So that's the main result. So to wrap up, what we have done is suggested in intuitionistic version of the full modal mu calculus that is expressive in the sense that it has this general universal modality, yet still shares many of those very nice properties with the classical mu calculus. So we have quite elegant, I think, game semantics, which are very clear. We have this guardedness property. We have a guarded, complete, cut-free, non-well-founded proof system. We have regular proofs and decidability because, well, the validity game is omega regular. It's also decidable. And the fact that the validity game is omega regular actually also means that we could use our normal founded proof system to get a cyclic proof system with a local soundness condition if you add in the right annotations. So there are now some nice general results, particular by Dominic Ware, showing how you can do this. We haven't done this, but at least we know that in theory it's possible if you add the right annotations. So in that sense, an expressive version that is still very well behaved. So some directions for future work is completeness also for the unguarded formula. So actually, I think, so this has been solved in the classical case as well. I think that the similar strategies should work here as well. I have not worked it out, but the completeness proof becomes a little bit harder because you do not get this sort of progress condition for free. when you work with unguarded formulas. Questions like interpolation, at least I know if we stick to the Lewis arrow, it will be difficult because this is still an open question. If you just look at the underlying, so fixed point free logic with just the Lewis arrow, but maybe if you're strict to the box fragment, it might be more doable. So extrapolating from this classical situation that we have so many nice properties of the classical mu calculus, maybe we could also have the nice property that there is a finite Hilbert excitation, as we know that we have cosine systems for the classical mu calculus, but I would say very big question mark because people who know the proof know it's very, very complicated and depends on the existence of certain normal forms in classical modal logic, so that might break intuitionistically. So I really don't know, that's why the question mark. And then adding diamonds, also very big question mark. So of course, this logic is still simple. So the underlying box fragment is little I, k, if you don't care about the Lewis arrow. And yeah, adding in diamonds will certainly break the whole idea of so forcing the pre-counter model to be an actual model, because then you have more complicated confluence properties. So this is, again, question mark if that is doable at all. That's all I want to say. Thank you for your attention.